another cycle. Another G sub 2. More growth, more in preparation for what? Mitosis. So, and for the longest time, people look at bacteria now they don't have a comparable cell cycle. That's what they do. Okay. We're going to talk about generation time here, and I'm trying to set the stage for this by talking about the phases that a cell will go through. Now, when a eukaryotic cell divides, how long is it long to get? Well, that's generation time. Maybe we need to define generation time. This is the time that it takes for a single cell to become two, or for a population of cells to double. So we can define it at the level, or we can define it at the population level. We've got a population of cells of 5 times 10 to the 6th. The time it takes for it to become 10 to the 7th is generation time. Or for one cell to become two cells, generation time. So what is the average generation time for a cell such as any eukaryotic cell? It's about 24 hours. So we can move ahead. All right, I don't want to waste your time. Okay. So did we talk about things that happen? Well, I know I talked about why it is that bacterial cells have a more rapid generation time, right? We talked about cellular enlargement occurs. Basically what's happening in G sub 1. Just as in eukaryotic cells, bacterial cells, this is a variable period of time. It may vary anywhere from, depending upon the bacterial cell, but it may vary from just a couple minutes to maybe 15 minutes. We call it the B phase. The B phase. Think of G sub 1 as comparable to the B phase. Then we have in eukaryotic cell cycle, we have synthesis, and we have the same thing in bacterial cells. Chromosomes are replicated. This is what we call the C phase. Now I say that's somewhat variable, but in actuality, the time for that chromosome to replicate from one genus to another is really pretty constant. There may be a little bit of differences in the enzymes that are involved in replication, but for the most part, given comparable sized chromosomes, it takes about the same amount of time. Unlike eukaryotic cells, however, once that chromosome is replicated, it almost immediately goes into a segregation, where the chromosomes are separated. But you don't have that G sub 2, where there's a preparation point. These cells are multiplying very rapidly, and it's ready to go as soon as those chromosomes have been replicated. In fact, it's oftentimes ready to go before they're replicated. And that's why we have to have that overlapping replication that we see. That's what we call the D phase. D phase. Formation, in this particular phase, the formation of a central transverse septum. That's what this is. This can take some time, and this is probably what limits the D phase. It's not important that you know these exactly like that, but I want you to realize that bacterial cells do have a very predictable cell cycle. Just as eukaryotic cells do, certain things happen during certain phases of that cell cycle. And you look at the variable time, variable time, variable time. When you look at the different types of bacteria from a genus standpoint, some of them are very rapid and some of them take a long time to divide because of the variability in each of these different stages. So the next chart then, over here we go. Quite variable. Quite variable. Okay, let's move ahead. Now I've got a chart. We'll talk about this chart. And this chart has a number of different things. You can see here we have colonies and microorganisms. You see some of these bacteria you've seen, you've not seen Bacillus microides, but you've seen its close cousin, Bacillus coli, you've not seen, I go back here to tuberculosis, but you see lactis. Different types of medium and different temperature and generation time. So what we want to do is we want to look at these two variables here. The nutritional adequacy of the medium and the environment temperature and how it relates to or influences the generation time. And the first thing we see here is that among these bacteria, the generation times vary wildly. Anywhere from 12 and a half minutes all the way up to roughly 850 minutes for mycobacteria. These we say, well, these are due to differences in the genome. To a certain point, that's true. So let's look at some of these combinations here. Here we see E. coli and Streptococcus lactis. Now, they're both grown in milk, so that particular variable is the same. And they're both grown at a temperature of 37 degrees. By the way, what is 37 degrees in Fahrenheit? Which is 98.6. No surprise that we incubate all of our clinical material typically at 37 degree incubation. That's body temperature. So that's 98.6. Now, look at the difference here in the generation. 12 and a half versus 26 minutes. Why? You say, well, it's E. coli, different genera. But why? Why do different genera have different generation times? Under the same conditions of growth, we have two different organs that have the same, have different, a lot of different generation times. But why? Why do those different genera, why does that make a difference? Well, we have to ask ourselves a more probing question. What do you suppose is the limiting factor that influences how rapidly or how slowly generation times take place? What is the limiting factor that determines how rapidly or how slowly one can divide? Not size. Although you get back to the surface volume, surface area. No. These are a little bit different. No, you're thinking, I like that. Okay, what do you think it is? No, not the size of the chromosome.
The enzymes, like the amount of enzymes that they can get into the cell.
That they can get into the cell.
Like that are there.
No, you're also an issue.
Streptococcus is very positive and
No. Somebody else mentioned that you're thinking. No. I'll tell you. How rapidly generate ATP takes energy. So how rapidly can they supply that energy? How rapidly can they supply that energy? And that doesn't differ between very positive and negative. In all of, well, from your experiences in biology, what are the mechanisms by which ATP can be generated? Two fundamental different ways. Aerobic respiration is one. We call that oxidative phosphorylation. Now, fermentation. You said anaerobic respiration, and most of you think that anaerobic respiration and fermentation are the same thing, and they could be more different. They could not be more different. There is a process called anaerobic respiration, but involves electron transport chain. It involves the reduction of materials other than oxygen, so it's anaerobic respiration. It's still respiration. Fermentation does not involve an electron transport chain. It is by definition anaerobic, doesn't involve oxygen. So we have fermentation on one hand, and we have oxidative phosphorylation or aerobic respiration on the other. Now, of those two processes, do they generate the same amount of ATP from volatile glucose? No, they don't. So which one generates more, which one generates less? Oxidative phosphorylation generates more. How much? How many ATPs for volatile glucose? ATP from fermentation? 2. It generates 4, but it has to kick back 2 because it's best 2. Remember that? So, if we're going to look at here, E. coli versus Streptococcus vacus. Streptococcus vacus is a totally fermentative organism. It is not capable of respiration. Whereas E. coli can be fermentative or it can be respiratory. And here it's going respiratory. So here now, by looking at generation time, we can say something about these organisms, their physiology. Now that may be an oversimplification, because there's obviously other things that go on. But clearly, in this particular case, they're growing in identically the same way. The only difference here is that one of them is only producing ATP, 2 ATPs per mole of glucose, while the other organism is generating 36. Actually, it's generating 38. Because eukaryotic cells can generate 36, but bacterial cells, because they don't have a mitochondria that they have to get that NADH across, they get 38. Okay. Now it can go fermentation, but it's just that okay, let's look at another one here. Here's E. coli. E. coli grown in broth. E. coli grown in milk. Same temperature, but there's a difference here in the generation time. Same organism, same temperature. The only difference here is the medium that we're growing in. So how might we explain the difference in generation time in this particular case? More sugar in the milk? Exactly right. Milk is loaded with sugar. This broth, I'm assuming, is strictly soy broth, TSV, which has just a little bit of glucose in it. But you've got milk sugar, you've got lactose. You've got galactose, and you've got glucose in there. You've got proteins in there. So this particular organism, this particular E. coli growing in milk, doesn't have to work as hard to get those metabolizable substrates. It's supplied to it in the medium, and that's reflected by a shorter generation time. Here we have E. coli growing in broth, but now we're looking at differences in the temperature. This is an environmental influence. Again, look at the difference in the generation time. 38 minutes at 20 degrees, 17 at 37 degrees. What should we attribute that difference to? What? Right. Well, but why is more energy being... Why at the higher temperature more energy be generated? Well, wait, I don't like that. We don't generate energy. First of all, we generate more heat. Metabolism depends upon what? Protein work faster, but they have to say another word. Why? Well. Molecules may be moving faster, but connected, but what is working faster at a higher temperature? Enzymes. Thanks. Enzymes. What are the enzyme differences here? Differences in the rate at which these enzymes are working. Okay. So the point of all this is that the generation time for a given organism can be influenced by the medium that you're trying to grow in and the temperature or other environmental conditions. We might substitute temperature for the presence or absence of oxygen, or the pH, or the presence or absence of salt, solid. Okay, we talked about this one. Mycobacterium tuberculosis. These organisms grow very slowly. And up to this point, I've